Okay, so now in this part of the lesson, we're going to learn about higher order derivatives and we're going to learn how we can use them in real life applications starting with physics. Now, we've learned the first derivative and we've learned that we can write it in a couple different ways. We've learned we can write it as y prime or f prime of x or dy dx. These are usually the most common forms, but you can also write it as ddx of f of x. And the least common form that you probably won't ever really see in your calculus class is you write large D sub x, so large D of x of y. But all of these are the same way, or all these are the different ways of expressing the same thing, which is the first derivative. Now, there's actually a second derivative, and what do you mean second derivative? Well, you can actually take the derivative of the derivative. So we call that a second derivative, and the way we represent that is we go y double prime or f double prime of x, or d with, we kind of write this as an exponent, but this is not d to the second power. When you write it in this form, that too represents the second order derivative. Likewise, you're going to write each of these with that 2 as sort of looking like an exponent. Doesn't mean exponent, but when you add that 2 like that, that represents you're taking the second order derivative. So you're taking the derivative of the derivative. And yes, you can actually take the derivative of the derivative of the derivative. You can get the third derivative. And you can basically just catch on the pattern now. We can write it as y triple prime or f triple prime of x, or d3 of y over dx of 3. But again, these are not exponents, but we can write higher order derivatives, meaning that we can take the derivative of the derivative of the derivative and keep on going. You can go to the fourth derivative. And when we get to this, you can technically still write it as, with those, with apostrophes, but it's probably better just to write a number like that. And fifth derivative if you want, sixth derivative, but in general, the nth derivative, we can represent it in any of these forms. Now it's like, well, what are those? Why do we need higher order derivatives? Well, what does it mean to be the derivative of a derivative? Well, the first answer is that it depends on what we're talking about. So we're going to start with probably the most common application that you're going to understand, and the most common application that you're going to see on your free response type problems on your AP exam, and that's dealing with how velocity and acceleration and how position are related when you're talking about like an object's motion. So remember that when we have an object, and we want to describe its position, we typically will use a position function where we make it equal to s of t. S is the common letter that we use to represent position at some point t. Now, what about velocity? Velocity is typically represented as v of t. Now, so what's the relationship between the position and the velocity? Well, position tells you where you are at some point in time, but velocity tells you how your position is changing at some point in time. So in other words, velocity is actually the derivative of position. So we can write v of t also as s prime of t. So velocity is the first derivative of position. Now, you probably all know about acceleration. When you're driving down the freeway and you got that open lane, you're probably going to be hitting that gas pedal, so you're going to be accelerating. So what does that mean? Well, acceleration, which we typically represent as a of t, describes how fast you're increasing your speed. Describes the rate of change of your speed. Now, I say rate of change because typically we think of acceleration as going faster, but acceleration is also technically when you slow down. So we say Acceleration is the rate of change of velocity, or acceleration is the derivative of velocity, is the first derivative of velocity, which means that if acceleration is the derivative of velocity, that means the derivative of velocity is the derivative of the position. So v prime of t is equal to s double prime of t. So this is an example of how we can use first and second order derivatives when we're dealing about some object's position. There's technically actually higher orders. They're actually, you probably heard of like the saying, snap, crackle, and pop, and jounce. Those are actually the higher order derivatives when we're talking about displacement. I'm not going to cover it yet. Let's first go over a basic application where we can apply these. So let's look at this example here. So here we got the moon that has no atmosphere. So when we have a falling object on the moon, there's no air resistance, and so we have that we can figure out its position with this equation: s of t being equal to negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. Now, first question is, what's the object's initial position? Well, initial position, what's s of t? That's when we're talking about position. But what's s of t when t is 0 at the start? So what's s of 0? Well, you plug in 0 into here, so you'll basically just get 0 plus 2, or just 2. So its initial position is that it's 2 meters above the surface, because we're talking about the height in meters. So we're talking about, again, the height above the ground. So we say 2 meters above the surface if you want to have a complete context. Now, how high off the ground is the object after 1 second? So we essentially want to know its position, since position talks about height above the ground. We want to find the position at t is 1. So we want to find s of 1. So we solve this or evaluate this for t is 1. And so then we just get negative 0.81 times 1 squared, or negative 0.81 times 1, plus 2, which is just going to give us 1.19 meters. So it's going to be 1.19 meters approximately above the ground after 1 second. Now, when does it hit the ground? So now we got to think a little bit. So when does it hit the ground? Well, what does that say about position? When the object hits the ground, how far is it above the ground? If it's hitting the ground, it's not above the ground. It's 0 meters above the ground. So when does it hit the ground? When is s of t equal to 0? Not s of 0, but when is s of t equal to 0? So we want to solve for the zeros of this. So we set this equal to 0. Negative 0.81 t squared plus 2. It's a basic algebra problem. We'll take away 2 and then divide by negative 0.81. And that'll give you t squared. And so then we take the square root of this. So let's leave that up to our calculator. So we go 2 divided by 0.81. And we take the square root of this, or raise this to the 0.5 power. And that's going to be about 1.57 seconds later. So it takes about 1.57 seconds to hit the ground. Okay, so far so good. Now part D. What is the object's initial velocity? Okay, so initial velocity, what's the starting velocity? So what's v at time equals 0? What's v of 0? We want to find v of 0. We don't have an equation for v of t, but we can find it because remember, velocity is a derivative of position. So to find v of 0, let's first find what v of t is in general. V of t is just the derivative of s of t. So we differentiate this. We get -2 times -0.81, which will be -1.62 t plus 0. So that's it. That's our equation for velocity. So then we find how fast it is going when t is 0. So we plug in 0 here. Well, let me plug it in. It looks a little weird. So -1.62 times 0. So it's 0. So it's going 0 meters per second, which means that it starts at a standstill. It's not like in motion when we start measuring, its position. So so the velocity is 0 at the beginning. Now, what is the velocity when it hits the ground? Okay, so that's different. And don't think like this means it's always going to be 0. Like really, again, it starts at a rate of movement of 0 meters per second. Now, when it hits the ground, or no, sorry, what is it? What's the velocity of the object after 1 second? So almost skipped one. So what's the velocity of the object after 1 second? We evaluate this for 1, which is simple. We just plug in 1. So we find v of 1, -1.62 times 1, which is just -1.62. So it's traveling about -1.62 meters per second. Now don't forget like what that negative means. We have a negative there because velocity specifies direction. Usually when we talk about speed is only rate of change. Speed doesn't account for direction, but velocity does. So this still has the same speed of 1.62. It's just the negative is telling you it's moving downward in this case. So just don't get confused by that. Now, part F, what's the velocity of the object when it hits the ground? So what's the velocity when it hits the ground? Well, it's going to hit the ground at about 1.57 seconds. So we want to find what is v of 1.57 going to be approximately. So v of 1.57, we plug in 1.57 into there. So we get -1.62 times 1.57. And use our calculator action. 0.62. And it's about 2.5434 meters per second, or I should say negative. It's moving, its velocity is about -2.5434 meters per second. When it hits the ground. Okay, now, G, what's the object's initial acceleration? So what is A of 0? So again, it's initial. So when t is 0, what's the acceleration at the start? So let's first find what the equation is for acceleration. And we find that by differentiating velocity, because remember, acceleration is the derivative of velocity, because acceleration describes the rate of change of velocity. So we calculate v prime of t, we take the derivative of this, and we get that v prime of t is just going to be -1.62. And we say meters per second squared. Now, I'm gonna talk a little bit more about why it's meters per second squared in the next problem. Because I know at first you're like, what's going on? So if you're a little uncomfortable with that, don't worry, I'll clear that up. Let's focus first on these last two parts. So the acceleration is -1.672 meters per second squared. So if we want to find its initial acceleration, it's just negative 1.672. It's saying that the acceleration is always negative 1.62 meters per second squared. It doesn't depend on time. So a of 0 is just negative 1.62 meters per second squared at the start. After 1 second, it's the same thing. It's going to be negative 1.62 meters per second squared. And when it hits the ground, yep, it's again negative 1.62 meters per second squared. Because again, the acceleration function is constant. It's always accelerating at this rate. It doesn't depend on the time. Okay, so I hope this introductory example helps. Again, really take careful time with going over these types of problems, especially if you haven't taken physics yet, because it's again, these are conceptual, but once you get it, you're going to see how easy it is. And I'm going to go over a more advanced example in the next video. So good luck, and I hope that helps.